Because my streaming stopped suddenly because of some power issue. Hello everyone out there. My streaming stopped all of a sudden because of some power issue, so I'm starting my stream all the way from the beginning again. Okay, I also changed the position of the board and my camera so that the board is little more clearly visible now. Okay, so we actually started with the word rest. When do we say the object is at rest? We say an object is at rest if the position of the object does not change with respect to time and with respect to its immediate surroundings. I have given the example of my camera and the board. With respect to the camera, the board does not move away. The position of the board does not change, okay, with respect to camera unless until I move it. So we say the board is at rest. Okay. Similarly, I will not move from here until I finish the streaming as I already said. So I am also at rest. The camera which does not move until the streaming is finished. My camera is also at rest. So everybody whose position does not change with respect to time, we say that object is at rest, and also with respect to its immediate surroundings. Now remember, when we speak about definitions, every word in a definition is important. Okay, I was saying immediate surroundings. Why is that immediate surrounding important? That we will know when we discuss about the next topic, that is motion, next heading, that is motion. Now, what is the meaning of this word motion? When do we say an object is in motion? Very simple. We said if the position of the body is not changing with respect to its immediate surroundings and it is not changing with respect to time, we said that object is at rest. If the position of the body is changing with respect to its immediate surroundings and it is also changing with respect to time, then we say the object is in motion. Okay, so for that I have given the example of, okay, let us discuss the example of a tree. Okay, there's a tree by the roadside and a person is standing under the tree. Now, with respect to the tree, the position of the person is not changing. So we say the person is at rest because he is not moving, he is standing under the tree. Okay, now if there is a kid who is running, okay, he is running. At the beginning of the time of observation, say at a 0th second, he is here. After 1 second, he came all the way till here. After 2 seconds, he is here. After 3 seconds, here. 4 seconds, he was here. So what is happening? After every 1 second, the position of the boy with respect to his immediate surrounding, that is the tree, is changing. Okay, as the position of the boy is changing with respect to the stationary surrounding or the immediate surrounding, we say the boy is in motion. So this is the difference between rest and motion. Now this motion is again classified. Okay, it is classified into translatory motion, oscillatory motion, rotatory motion. Okay, this rectilinear and curvilinear actually come under translatory motion. So to avoid the confusion, let me write this here. Okay, under translatory motion we have rectilinear motion and curvilinear motion. Now what is, okay, this is classified on the basis of the path taken. If the object is traveling along an undefined path, irregular, haphazard, okay, undefined path, then we say the body is undergoing irregular motion. A wasp which is flying, it does not follow one regular path. A bee or a housefly which is flying, it does not follow one regular path. Okay, it just goes, it takes a random path like this, and finally it comes back to initial position maybe. So this kind of motion wherein the path is not a well defined one is called irregular motion. Now coming to the other one, if the path of the object is well defined, okay, the path of the body is properly following a regular path, like it's a well defined path, then we say it is regular motion. Now that regular motion is again classified into translatory, oscillatory and rotatory motions. Yes, now what is translatory motion? Translatory motion is one in which a body as a whole is traveling from one point to another point. Okay, if the body is traveling from one point to another point, then we say it is translatory motion. Suppose I am running. Assume I am running. I am in translatory motion because from the starting point to the final point I am moving. Okay, as a whole, completely. Okay, so it comes under translatory motion. Now this translatory motion is again classified into two types. One is rectilinear motion, the other one is curvilinear motion. Now what is a rectilinear motion? Rectilinear motion is something which many of you have heard is in the topic of light, when we say light travels along a straight line path, it exhibits rectilinear motion. Yes, rectilinear motion means along a straight line path. Here, if the object which is under study is traveling along a straight line path, then we say it is undergoing rectilinear motion. I take a ball and I roll it along the floor, okay, and assume that it is traveling along a straight line path, then we say it is undergoing rectilinear motion. Suppose I go to a bowling club, I take the ball and I throw it along the gutter by the side, then yes, along the gutter it travels in a straight line path, so it is rectilinear motion. I fire a bullet out of gun. This is interesting. I fire a bullet out of gun. For the first few meters of distance, it travels along a straight line path. So from here to here, it is rectilinear motion. After that, it takes a curve, right? So from this point to this point, it is taking a curve. So this is called curvilinear motion. Okay. So by this we understand what is rectilinear and what is curvilinear. Rectilinear means along a straight line path. Curvilinear means over a curved path. Okay. Now, both are coming under translatory because the object as a whole is moving. Now coming to oscillation. Oscillation is something which we are very familiar if we have those antique wall clocks in our house. Okay, those have a pendulum, which give a very good example for oscillatory motion. Suppose this is the string by means of which I am suspending the pendulum, and this is the bob. Remember, from the point of suspension till the center of gravity of the bob, from the point of suspension till the center of gravity of the bob, we call it as length of the pendulum. Okay, and this position where the pendulum is at rest, okay, the position where it is freely suspended and it is at rest, we say it is the mean position. It is the mean position. Now what I do, I would pull the pendulum towards one side and I release it. So let us assume I pulled it till here. Okay, so this position is called extreme position. So we have the mean position, and now we know what is extreme position. Extreme position is nothing but the after the object has undergone a maximum displacement, okay, from its mean position, then that position is called extreme position. Now from there, when I release it, remember, I'm not pushing it, I'm just dropping it, I'm releasing it. When I release that, it moves down, it comes to its mean position, and after that it will go to extreme position on the other side, like this. So here what is happening, this is one extreme position, this is an extreme position. So if the body is undergoing a complete 360, that means from extreme position to mean position, from mean position to the other extreme position, so Q, and from there it is coming to mean position, and from mean position it is coming to the initial position. So that to and fro motion, wherein it is completing 4 quadrants, okay, is called oscillation. Okay, the to and fro motion of an object along a path, along the same path, is called oscillation. Okay, now this oscillatory motion is always directed towards the mean position, accelerated towards the mean position, and this comes under simple harmonic motion. Now coming to another small, what we say, a classification of this oscillation, it is vibration. There are many people who actually get confused because both vibration and oscillation have the same definition, to and fro motion of the object or particle. Let me tell you what actually brings about the difference between vibration and oscillation. In case of oscillation, the entire body, starting from, for example, I have taken pendulum, starting from the point of suspension till the center of the bob, the entire pendulum is undergoing to and fro motion. So we say it is oscillation. On the other hand, if I take a tuning fork, I hope you have seen a tuning fork before. Okay, this is how the tuning fork looks. Okay, now if I strike this, only this part of the tuning fork will be undergoing to and fro motion. The remaining part, that is the stem of the tuning fork, does not vibrate. Okay, it does not undergo to and fro motion. So this we call it as vibration. If the entire body is undergoing to and fro motion, we say it is oscillation. If only a part of the body is undergoing to and fro motion, we say it is vibration. That is the difference between vibration and oscillation. Now coming to rotatory motion. Rotation means spinning about its own axis. Okay, in your lower class geography, you must have learned that Earth undergoes rotation as well as revolution. Revolution means moving all around the sun in a path called orbit, specified path called orbit, and rotation means Earth spins on its own axis. That is called rotation. Yes, if a body is spinning on its own axis, about its own axis, then we say it is rotatory motion. And this is exhibited not only by the Earth, by the spinning top also. Okay, when a top is made to spin, the entire body is actually spinning on one point. Okay, if this is the top, the entire top will be spinning on one tip of the needle. Okay, so whose axis is like this. Remember, the spinning will happen only if it is maintaining the symmetry. If the symmetry is not there, then the momentum is not conserved and it would be falling down immediately. Okay, it should be having a proper speed and it should be having a symmetry over the axis. Only then it will spin. Okay, and this motion is called rotatory motion. Okay, now coming to the next part. The terms which are related to the topic motion. Okay, the first term which comes into our mind is distance. Let us assume this is a point A, okay, and there is another point B. Now, an object which started the moving, which started from a point A, is not going straight from point A to point B. It has taken a path like this. Okay, so this total length of the path covered by the body is called the distance. So distance is length of path. Okay, distance is the total length of the path covered by the body. Okay, now what is displacement? The second term is displacement. Displacement is the shortest and the straightest path. Okay, of course, if it has to be shortest, it must be straightest path. The shortest and the straightest path between A and B, okay, is called displacement. Rather, I would say displacement is the change in the position of the object. Initially, the object was here, then it came here, so there's a change in the position, and that change in the position of the object is called displacement. Okay, both the distance and displacement are measured in meter. Now, here we come across a term that is scalar. But let me first write the topic which we discussed: displacement. Okay. Now, all physical quantities are classified into two types depending on their direction, whether they possess any direction or not. If they are having any direction, okay, if they have a specific direction along which they are moving, then we call them as vector quantities. And if they are not having any specific direction, then we say they are scalar quantities. Now look at this. If I look into that yellow color line I have drawn from A to, no, green color line I have drawn from A to B, it is not having any specific direction. For a certain point of time, it was straight up, then it is curved towards the right side, then it is down. So all these suggest that it is not actually following a specific path. So this is why we call it as a scalar quantity. So distance is a scalar quantity. On the other hand, displacement, we are saying it moved from A to B straight. Okay, so from A to B along a straight line path. So there is a specific direction here. So we say it is displacement, and that displacement, because it is having a specific direction, which is a vector quantity. Okay, so like this we are having scalar and vector quantities. Now, coming to the next term, speed. Okay, speed is the rate at which an object covers a path. Okay, if a body is traveling from one point to another point, okay, the time taken by that object to cover that path is called speed. Okay, so we define speed as the rate at which the body is covering the path. So The total path is nothing but the distance, and whenever we use the word rate, we have to divide by time. So it is time, or and it is distance. So we say speed is a distance over time, okay, or simply distance by time. And if we look into units, the unit of distance is a meter and unit of time is second. So speed unit is a meter per second. Now coming to the next word, velocity. Velocity is defined as rate of change of position of an object. Okay. Now change of position of an object is nothing but displacement. There is a change in the position of this object from A to B. There is a change in the position of the object. The change in the position of object per given time is called velocity. So we define velocity as rate of, that means divided by time, change in position. So that is displacement. This is also measured in meter per second. Now let us see the representation we use. We use the term V, the letter alphabet V, to represent velocity. Okay, and we use the word S to represent displacement. Now the same change in the position we represent with delta S. Delta is the symbol for change. Okay, up to grade 10. If you write it as displacement by time, that is S by T, yes, it is accepted and it is correct. It is not wrong. Okay, for standards which are more than 10, plus 1, plus 2 and above, we represent that with delta S. S represents a position and delta represents change. So delta S is change in position divided by delta t, which is change in time. So velocity is given by delta s by delta t, or simply s by t. Okay, this is only a difference in the representation, but the value does not change, so you don't have to worry about it. Now coming to the next term, that is acceleration. See, acceleration is defined as rate of change of velocity. Now, do we experience acceleration at all? Definitely yes. If I take an object at this position and I drop it, for example, I have taken some object which I have, okay, and I dropped it. Immediately when I drop it, its velocity is 0. Okay, but slowly what happens as it is moving down, its velocity keeps on increasing. Okay, its velocity keeps on increasing. So there is a change in velocity. That means that object is getting accelerated. Let me tell you an interesting fact which I also heard when some great people talking over a television show said, if you go to the top of the Empire State Building and drop a $1 coin from there, by the time it reaches the ground, it seems it would gain so much velocity that it can pierce through the skull of the person standing under that. So imagine how much speed it must have gained. Okay, so that means it is getting accelerated. Okay, now this acceleration is defined as rate of change of velocity, as I said. So change in velocity, that is v minus u, I will write if v is the final velocity and u is the initial velocity divided by time. Okay, so change in velocity divided by time, or I can write it as delta v by delta t. Delta v, change in velocity. Delta t, change in time. So delta is representing change, so we don't have to, as delta represents change, we don't have to worry about we don't have to get confused. Delta means change. That's it. So change in velocity per change in time. So that is giving us acceleration. Now these are also again classified. Okay, we have uniform and non-uniform. Let us know how. We have uniform speed. We say an object is traveling with uniform speed if it is covering equal distance in equal intervals of time. For example, say I will use the same figure. Say from here till here, the distance is 1 meter. So it is covering this 1 meter in 1 second. And from here to here, it is another 1 meter. In the next 1 second, that means by the end of 2 seconds, the distance covered by that object is 2 meters. That means in 1 second, 1 meter. After 1 more second, again it covered only 1 meter. That means by the end of 3 seconds, it is covering a distance of 3 meters. For 1 second, 1 meter. 1 second, 1 meter. So like that, for equal intervals of time, the interval of time being 1 meter, for equal intervals of time, it is covering equal distance. Then we say it is uniform speed. Okay. Now what is non-uniform speed? Suppose if for the first 1 second it covered 1 meters, and the next second if it has covered 3 meters, that means first second 1 meter, in the second it covered 2 meters, so total 3 meters. In the third second it covered 6 meters. That means what is happening? It is not covering equal distance in equal intervals of time. Then we say it is non-uniform speed. Now what about velocity? The term, instead of distance we will give displacement. That is the only difference. We use the word displacement in place of distance. Okay. Now distance can be equal to displacement if the body is traveling along if a body is traveling along a straight line path, then we say it is, then we can say that distance is equal to displacement. So let me say once again, if a body is covering equal distance in equal intervals of time, then we say it is uniform speed. If a body is undergoing equal displacement in equal intervals of time, then we say it is uniform velocity. Similarly, if a body is undergoing unequal distance, if a body is covering unequal distances in equal intervals of time, then we say it is non-uniform speed. Okay, if a body is undergoing unequal displacement in equal intervals of time, then we say it is non-uniform velocity. Okay. Now now based on this, can I say if a body is accelerating, it is undergoing unequal velocity or say non-uniform velocity? Definitely yes. If a body is covering unequal displacement in equal intervals of time, then we say it is accelerating because there is a change in the velocity per unit time. Okay. Now coming to the next part, acceleration. Yes, can acceleration also be uniform and non-uniform? Definitely yes. Okay. If the change in velocity in given time, if a body is undergoing equal change in velocity in equal intervals of time, then we say it is uniform acceleration. You must have come across this word that acceleration due to gravity is uniform. Definitely yes. Okay, if a body is taken to a certain height and there it is a drop, it will be accelerating uniformly. We say it is 9.81 meter per second square, and for our convenience in calculation, we sometimes take it as a 10 also. We take it as 10 only if it is mentioned in the question, examination point of view. Or else it is 9.81 meter per second square. So, now if a body undergoes equal change in velocity in equal intervals of time, then we say it is uniform acceleration. On the other hand, if a body is undergoing unequal change in velocity in equal intervals of time, then it is non-uniform acceleration. There is something I would like to tell you. There was an experiment that was conducted in a very huge laboratory wherein a building which is almost a three-storied height, okay, is evacuated. A chamber which can be three-storied height was evacuated, and a bunch of feathers and a bowling ball were dropped from a certain height, and those two are also dropped using an electronic clipper which releases both at the same time. It is noticed that both the bowling ball and the feather reached the bottom at the same time. Okay, that means that acceleration due to gravity is same on all objects irrespective of their masses. Okay, now what is making the feather to land slowly under normal circumstances? It is because of the air resistance. Now, as we are talking about speed and velocity, let me also tell you about a term which we don't often come across. That is called terminal velocity. Terminal velocity is not related to anything which is the movie name. It has nothing to do with any Hollywood movie. See, if I take an object and drop it from a certain height, as it is coming down, its velocity should increase. If its velocity is increasing, then the resistance offered by the atmosphere also increases. Okay, so it is exerting force in downward direction, then air resistance will be acting in upward direction. These two will become equal at one point of time. Okay, now what happens after that acceleration? The body will start traveling with uniform velocity. Okay, that means initially the velocity will increase and then it will become uniform. So that velocity acquired by the body is called terminal velocity. I'm repeating this. If an object is dropped from a certain height, initially its velocity will increase because of acceleration due to gravity. After a certain point of time, the air resistance would be acting on it. With the increase in velocity, the air resistance also increases, and thereby it would start decelerating, and finally it will start traveling with a uniform speed, and that uniform speed acquired by a freely falling body is called terminal velocity. Okay, this we seldom find in our textbook. Okay, now when we speak about velocity, let me also tell you, we travel on vehicles, on different vehicles, two-wheelers, three-wheelers, four-wheelers, 10-wheelers, a bus, okay, multi-axle bus. So we see a meter which has a pointer showing at different big numbers. What is it actually showing? We call it as a speedometer. Okay. Now what is it actually showing? Is it showing us the speed of the vehicle? If it is showing us the speed of the vehicle, is it showing us the speed at that point of time, or the maximum speed that is required, or the speed at which we can travel? Here, these three terms are totally different. The speedometer of a vehicle actually shows us the velocity or the speed of the vehicle at that point of time. Okay, so it is the speed of the vehicle at that point of time, and that is called instantaneous velocity. So velocity acquired by the body at a given point of time is called instantaneous velocity. Okay, So this instantaneous velocity is again like depending on the time what we are taking into consideration. It can be initial velocity, which is denoted by the letter U, small letter u. Remember, capital U represents potential energy, so we use small u. Okay, and final velocity, small v. Okay, my handwriting makes it look like a Greek alphabet nu, but it is small v. Whereas capital V, which is the total displacement by total time, is called the average velocity. So average velocity is given by the total displacement divided by total time. U and V are instantaneous velocities, the velocity acquired by the body at that given point of time. Okay. Now, all these have the same unit because those are velocities. They are measured in meter per second, and all these are vector quantities. No doubt about it. Okay. Now, we actually represent motion with help of graphs. We have graphical representations, which makes the study of that easy for us. Okay. So, let us look into different types of graphs which are possible when we are discussing about motion of an object. First one, displacement time graph, ST graph. Okay. Now, I take displacement along x-axis, okay, and time along, excuse me. Okay, I take time in seconds and the position of the body, okay, along y-axis. Okay, if the graph plotted is parallel to x-axis, what does that represent? It is very simple. All we need to do is use a little bit of logic. At the end of 1 second, the object is say 2 meters away. After 2 seconds also it is 2 meters away. After 3 seconds also it is 2 meters away. That means after, like, even though the time is passing by, the position of the object with respect to its initial point, origin, is not changing. Okay, as its position is not changing, we say that object is at rest. So in a displacement time graph, if the graph plotted is parallel to x-axis, then the object is at rest. Okay. Now I take another graph. The climate is so loving now, it started drizzling. Okay, so again I take displacement along y-axis and time along x-axis. Now the graph plotted turned out to be like this. Okay, assuming this to be a straight line. Okay, considering my stable hand and excellent drawing skills, assume this to be a straight line. Now, what is happening here? Is it at rest or in motion? Undoubtedly, it is in motion because we can see at the end of 1 second, it is at this point. After 2 seconds, it is here. After 3 seconds. So what is happening? With the passing of time, the position of the body is changing. Okay, so we say it is in motion. Now again, let us try to read about it in detail. After regular intervals of time, the change in the position is also same. Okay, so that means it is uniform motion. On the other hand, if the graph plotted is like this, now can we call it as regular? Definitely not, because see, I divided that into equal parts. At this point, yes, the object is here, and at this point, and if I draw a line like this, is here. If I draw a line like this, I extend it, it is here. See, for each interval of time, the displacement undergone by that is not constant. So we say it is non-uniform motion. Okay, so it is non-uniform motion. So these are the graphs which we can get. Let me draw one more graph. See, I again take time along x-axis, displacement along y-axis, and the graph I plotted, it came like this, parallel to y-axis. When we can get a graph parallel to x-axis, why can't we get the graph parallel to y-axis? Is it possible? Definitely not. I will tell you why. See, say this is the second unit of time or the second point of time, maybe the second. Okay, here at this point, say it is 1 unit away from the origin, say 1 meter away from the origin. At the same point of time, it is 2 meters away from the origin. At the same point of time, it is 3 meters away from the origin. Okay, that means what is happening? At the same time, the object is existing at 3 different points, which is as of now physically not possible. Come on, the body is not undergoing any teleporting. Okay, even in teleporting also, the object disappears, vanishes here and goes there. Here it is not the case. At the same point of time, it is there in 3 different positions, which is not possible. So we say this does not exist, this does not happen. You will never get a graph wherein the object exists at 2 different points at the same point of time. So these are displacement time graphs. Now let us look into velocity time graphs. I'm sure half of my streaming time is because of this rubbing of board. Okay, so next, velocity time graphs. See, in case of velocity time graph also, we take time along x-axis and the velocity along y-axis. Okay, so time in seconds along x-axis. If the graph plotted is parallel to x-axis, what does that mean? If the graph plotted is parallel to x-axis, it means that at the first interval of time, it is having a velocity say 2 meters per second. After 1 more second, the velocity is still 2 meters per second. After the third second also, the velocity is 2 meters per second. That means it is having the same velocity even with the passage of time. So we say the body is traveling with uniform velocity. Okay. Now, what if the graph plotted is like this? Like this. Okay. Now, here what is happening? At the first interval of time, the body has traveled 1 unit. At the second interval of time, another 1 unit. At the third interval of time, another 1 unit, like that. For equal intervals of time, it is undergoing a change in velocity. So there is a change in velocity, that means it is being accelerated. Fine. Now, how is the acceleration? We have seen that for equal change in time interval, there is equal change in velocity. So if there is equal change in velocity in equal intervals of time, then the body is in uniform acceleration. So we are having a body which is being uniformly accelerated. This graph is uniform acceleration. Now, what if the graph comes the other way around? It is not that always the velocity increases. Sometimes we may have the velocity decreasing also. For example, see, I have a graph like this. That means initially it is having a larger velocity, much higher velocity, and slowly it is slowing down. As the time passes by, its velocity is decreasing. So, at the the first part of at the end of the first interval of time, it has this velocity. At the end of the second interval of time, we can see here at the end of the third interval of time, like this, what is happening? We can see that there is a change in the velocity. That also for equal time intervals, the change in velocity is also equal. So we say it is uniformly accelerating. Change in velocity is same. Okay, we said if it is change in velocity, there is acceleration. But here, the change in velocity is negative. Instead of increasing, there is a decrease in velocity. So we say uniform retardation. So this is uniform acceleration because final velocity is more than initial velocity. We call this as uniform retardation because final velocity is less than initial velocity. Okay. Now, had this line or the graph plotted not been straight, then what might have happened? Had this graph plotted not been straight, then what might have happened? We say it is non-uniform. Okay, it is non-uniform acceleration. Okay, if this graph wherein initial velocity is less and final velocity is more, see the graph which I plotted has turned out to be like this. So what is happening? Definitely velocity is increasing. But that increase in velocity is not constant. Initially it is less and slowly it is increasing. It is skyrocketed. So we say it is non-uniform acceleration. Similarly, if the graph plotted here comes like this, like a curve, then we say it is non-uniform retardation. Okay, so these are all displacement time graphs. Now we have one more quantity when we speak about motion, that is acceleration. What about acceleration time graph? Remember, all these things which we are learning actually come under kinematics. Anything which is related to motion is divided into two parts, dynamics and kinematics. If we are considering the motion of an object, that means its state of rest, state of motion, velocity, distance, displacement, acceleration, speed, uniform speed, non-uniform speed, all these things, it all comes under kinematics. Remember, in due course, we never come across the term force. We never come across the cause of motion. Why the body is moving, that we will not consider anywhere. And so we call it as kinematics. On the other hand, if we are considering the cause of motion also into consideration, we are considering even the cause of motion. That means force, obviously. A body starts moving only because a force acts on it. So if we are considering the cause of motion, then it is dynamics, which we will be learning about maybe in the next video. Okay. So now coming to acceleration time graph. Here there is nothing much. Okay, if I take time along x-axis in seconds and acceleration along y-axis. If I get the graph like this, parallel to x-axis, it means it is uniform acceleration. On the other hand, if I get the graph like this, okay, this non-uniform acceleration, the acceleration is increasing. Very simple, quite simple. Okay, now if the acceleration is negative, that means it is coming below x-axis. Then we say it is retardation. So these are the different graphs we come across when we speak about motion chapter. Now, in this motion chapter, we also have some equations of motion using which we will be finding the unknown quantity. You must have come across three equations of motion, right? V is equal to u plus at, S is equal to ut plus half at square, and v square minus u square is equal to 2as. These three are the equations you might have come across. But there is also a fourth equation of motion. We will discuss all these four equations of motion both by algebraic derivation as well as by graphical derivation. Of course, graphical derivation we will do only for three equations of motion. Okay. Now, coming to first equation of motion, we have by definition of acceleration, acceleration A is equal to v minus u by t. Remember, this v and u are instantaneous velocities, not average. Okay, instantaneous velocities. A is equal to v minus u by t. Now, upon cross multiplying, I get at is equal to v minus u. Okay, if I bring u to the other side, making v as the subject of the formula, I get v is equal to u plus at. So this is the first equation of motion. This is very simple. It should be a cakewalk. Okay, we have the formula of acceleration. A is equal to v minus u by t. Upon cross multiplying, we got at is equal to v minus u. Now, we made v as the subject. In due course, I have sent u to the other side. This is minus u. This minus u, when crosses equality, it becomes plus u. This is how I remember mathematics. Okay, the operation becomes opposite. Plus, minus, addition, subtraction, multiplication, and division. These four operations change to their opposite when they cross equal to. So, this minus u becomes plus u, so u plus at is equal to the final velocity v. Now coming to the second equation. In case of second equation, we will define average velocity. We already defined average velocity as the total displacement divided by total time, s by t. And we also defined average velocity, or we can write average velocity as the sum of velocities divided by 2. It is as simple as that. Now, from the first equation of motion, we have v is equal to u plus at. So let me substitute that here. I get s by t is equal to, in place of v, I write u plus at plus u divided by 2. So I can write s by t is equal to u plus u is 2u plus at divided by 2. Okay. Now, because this operation is addition, denominator belongs to both the terms. So, s by t is equal to 2u by 2 plus at by 2. Here 2 and 2 gets cancelled. So, I am left with S by t is equal to u plus at by 2. So S is equal to u plus half at into t. Remember this t, when it is brought to the other side, it should be multiplied with each and every term. So I get S is equal to u into t, that is ut, plus half into a into t into t is t square. So S is equal to ut plus half at square. This is the second equation of motion. Now coming to the third equation of motion. Where do I write that? I would rub both equations to accommodate the third one. So coming to third equation of motion. We have from formula acceleration A is equal to v minus u by t. From this I can write t is equal to v minus u by a. Similarly, I have total displacement by total time is nothing but v plus u by 2. Now what I would do, I would send this t to the other side. Okay, so S is equal to v plus u into t divided by 2. Now time, I have it as v minus u. So I would substitute that. So v plus u into v minus u by a divided by 2. This is equal to S. Now 2a, I will bring it to the other side. These two being denominators, that is they are dividing, upon crossing equal to, they will become multiplication. That makes it 2as, that is equal to v plus u and into v minus u. As far as my memory of mathematics goes, this is in the form of a plus b into a minus b, which is a square minus b square. So v square minus u square. So this is the third equation of motion. Okay. So these are the three equations of motion which we are actually very familiar with. Now equation of motion, okay, which many people don't recognize it, or maybe they don't care it by much, okay, which will be getting in your higher classes, and this is not given that importance because it is not very much used also. Okay, before knowing that, let me first draw a figure. Let us assume there is an object which started traveling from here till here. So the total distance covered by that is S. The total distance covered by the object in n seconds is S of n. Okay. Apparently this color is not supporting. So S of n is the total distance covered by the object in n seconds, or the displacement undergone by the object in n seconds. Then Sn is the displacement undergone by the object in the nth second. How we will get that? If I take Sn minus 1, that is displacement undergone by the body in n seconds, displacement undergone by the body in n minus 1 seconds, then what will it give me? I will tell you how. The displacement undergone by the body by the time it came here is n seconds. Okay, and by the time it covered, the time was only n minus 1 seconds, it came till here. So n minus 1 seconds. So this distance or this displacement is what we are trying to find. The time, the displacement undergone by the body in the nth second. That means if the body is traveling a certain distance up to 4 seconds and it has covered a little more distance in the 50 seconds. So the time, the distance that is covered between this fourth and reaching the fifth, 4.0012, that displacement undergone by the body is Sn. This is what we are trying to find. How can you find that? Very simple. Sn is equal to, that is total displacement undergone by the body in the nth second is equal to Sn, that is displacement undergone by the body in n seconds, minus S of n minus 1, displacement undergone by the body by n minus 1 seconds. So this is what we are going to follow. Now for this we already have an equation of motion. Okay, that is the second equation of motion, which says S is equal to ut plus half at square. Instead of t, we are using the representation n here, which is not a very big problem. So displacement undergone by the body in the nth second is equal to S, that is u n plus half a n square minus in the n minus 1th second. Okay, so it would be u into n minus 1. In place of n, I am writing n minus 1. That's all, because I want to find the displacement undergone by the body in n minus 1 second. So u into n minus 1 plus half into a into n minus 1 whole square. So this is what we have written. Okay. Now let us try to simplify this. It will be un plus half an square minus, I leave the bracket before I could furthermore simplify this, un minus u, because u into minus 1 is minus u, plus half into a into n minus 1 whole square. Okay, shall we open the brackets now, or shall we simplify this n minus 1 whole square also? Let us simplify. At any point of time we have to simplify this. So un plus half an square minus un minus u plus half a into, this is in the form of a minus b whole square, so it will be n square plus 1 minus 2n. So I will write the same here, 1 by 2 a n square plus 1 by 2 a minus 1 by 2 into a into 2n. So this is how we are writing. Now let us simplify this. So it is un plus a half an square minus, I am opening the brackets to make it further simpler, un plus half an square minus un, minus into minus plus u, minus into plus is minus half an square, minus into plus is minus half a, minus into minus is plus half. Okay, we can actually cancel this. 2 and 2 gets cancelled, so there is no half here. Minus into minus is plus an. Okay, now we have plus un and minus un that get cancelled out. plus half an square and minus half an square, that get cancelled out. So we are left with u minus half a plus an. Okay, so this will be u plus, I take a common from these two, a into and minus half. So this is the fourth equation of motion, which is giving us the displacement undergone by the body in the nth second. Remember, it is not at the end of n seconds, it is the nth second. Okay. Now coming to equations of motion which are derived using the graph. Okay. Now there is a graph which we should take into consideration. Let me draw that on the board. And yes, there is one important consideration here. All these equations of motion are valid only if the body is undergoing uniform acceleration. These are valid only for uniformly accelerated bodies. Okay, please do keep that in mind. Now the graph I would plot is somewhat like this. I have a velocity time graph in which I take time t in seconds along x-axis and velocity v in meter per second along y-axis. Okay, now a body is traveling at the point when we started observing. It is already having a velocity u. I name this as a point A. Okay, at that point of time, it is having a velocity u. As I said, it is uniformly accelerating. A straight line graph is plotted. Now, its velocity is v meter per second, and by that point of time, it is t seconds. So we have like this different intervals of time. Now I take this as t, the time for which by which the velocity has changed from u to v is t seconds. This is the origin O. So initial velocity, okay, I can name this as B, I can name this as C, I can name it as D, E, whatever. Any alphabet you can choose, as long as you are clear with the concept. The alphabet you choose is not going to matter at all. Okay. Now, coming to the first equation of motion, deriving the first equation of motion using this graph. We have the definition of acceleration. Acceleration as change in velocity divided by time. So acceleration is change in velocity is what we said. Change in velocity. What was the change in velocity? It is changed from u to v. Okay. So that same thing is explained like this. Initial velocity is from O to A. Okay, so initial velocity is O to A and it changed from OB. So OB minus OA divided by the time taken. Okay, T. So how much is OA? It is U. How much is OB? It is V. So V minus U divided by T is A, and we got V is equal to U plus AT by changing the subject of the formula to V. It is a direct one. Okay. Now coming to the second equation of motion, wherein we are asked to find, we have to find the displacement. Remember, displacement can always be obtained by finding the area under the graph. Now this graph what I have plotted is actually in shape of a trapezium. Is it not in shape of a trapezium? Okay, now this trapezium is having OA and EC as parallel sides, but EC is nothing but OB. Okay, so EC and OB are equal, so we can write this. Okay, first of all, we write the formula. We know the total displacement S is equal to area under graph, Okay, so area under the graph, in this case it is a trapezium, so it is a half into sum of the parallel sides, that is OA plus EC, sum of the parallel sides, into height, that is T. Okay, so it is half into sum of the parallel sides OA plus this EC is nothing but OB. So in place of EC I write OB into T. So half into OA is nothing but U plus O is nothing but V into times T. Okay, so S is equal to half into UT plus half into VT, or rather again I can write T is equal to change. Okay, so we have V is equal to U plus AT, but V again is from equation of motion, first equation of motion, we can write V is equal to U plus AT. Okay, so to eliminate V, so we can do that. So half into, may this sketch rest in peace, half into U plus AT into T. So S is equal to half into 2U plus AT into T. So S is equal to UT plus half AT square. You know the derivation, because upon this being a plus, we should write this 2 to both. So it will be half into 2U plus half into AT, and this T multiplied to both, it gives T and square here. 2 and 2 gets cancelled, so we are left with UT, which I wrote here, half AT square. This is the second equation of motion. Similarly, coming to the third equation of motion, it is again the combination of both second equation of motion and third equation of motion, which is also very simple. Again, we are considering the same thing, area under the graph being the displacement. So I have SC is equal to this area of the trapezium, that is half into height into sum of the parallel sides, that is OA plus EC. Okay, OA plus EC. So that is half into time into OA plus EC is nothing but OA plus OB. Okay. Now we have time. From the formula of acceleration, we can write T is equal to V minus U by A. Because A is equals to V minus U by T, I can write T is equals to V minus U by A. I will substitute that here. I get S is equal to half into, in place of T, I will write V minus U by A into OA is U plus OB is V. So again, it is a direct calculation. We got SC is equal to 1 by 2A into V minus U into V plus U, V square minus U square. So we get V square minus U square is equal to 2AS. This is the third equation of motion using graph. Okay, so this is all about motion chapter and also motion along a plane. Okay, motion along a straight line, not even in plane. Okay, these topics are sufficient until your +1. Okay, it started in grade 6 for ICSE students as well as the state syllabus of Andhra Pradesh and CBSE students. The motion, the concept of motion and rest, and then it proceeded stage by stage till +1. That is your first year. Okay, and by the time you reach +1, the same chapter you will be learning under the heading motion along a straight line. Now remember, as we are talking about velocities, there is one point I would like to mention. If there are two bodies which are traveling parallel to each other along the same direction, then depending on their velocities, they can be at rest with respect to each other, at rest with respect to each other, or they can be in motion. If both are traveling along the same direction side by side parallel to each other with the same speed, then we can say these two are at rest. Okay, with respect to each other. If we come across a question wherein a train crossed a lamp post, then the distance should be taken as the length of the train. The length of the train will be the distance that should be covered. On the other hand, if they say a bridge is crossed by a train, then the total distance covered will be the length of the train plus the length of the bridge. We add velocities if they are traveling along the same direction, and if they are traveling in opposite directions. Sorry, we add the distance if both are traveling along the same direction, and we subtract the distance if they are in opposite direction. Whereas in velocity it is different. If they are traveling in opposite direction, their velocity is actually increased, and the time will be always shorter. Okay, so have a nice time until we meet again in the next video. Bye bye.